The title of this presentation is Overview and Concluding Remarks. To begin with the presentation overview, the last part of this series, I'm going to be describing and reiterating some of the overview remarks in the overview slide from the first presentation of the series so that we can kind of get ourselves into the type of position and frame set and mindset that we were in previously when we hadn't made several associations about noisy error correcting codes, in addition to how this relates to mapping into the authenticated space with suitable decoding protocols, as well as the converse result on the bit transmission rate that we've been discussing at several points, pretty much every presentation of the series, obviously. So we're going to introduce encoding, decoding, transmission, and authentication protocols that are resilient to the presence of noise. And we're doing this so that we can resolve an open question in the literature with regards to the converse result on bit transmission rates. Such rates are important for, one, determining whether there are physical fundamental limits or limitations for error correction and authentication. And I mean, obviously, this is resulting very much to a topic that's of use for, I guess, what we could call the industrial quantum computing sector, more the, industry side of things rather than just purely theoretical research, because really determining whether these types of error correction and authentication protocols or even false acceptance protocols to minimize the probability of a quantum algorithm or an agent who is making use of quantum information to be able to try to detect errors so that they can make use of proposed or maybe pronounced features of sources of quantum advantage that are intrinsically from the quantum side or aspects of information, because it's also really helping us determine, as we're saying in the second bullet point, how previous work on quantum information theory can be of use. And I really described a lot of potential applications that I'm also going to further delve upon in terms of the algorithmic sense more near the end of this presentation of this series for the overview and concluding remarks part. And altogether, this was allowing us to elaborate further upon the paradoxical nature of quantum physics. So it's just basically given the fact that even though we obviously can't make all of the types of measurements that we would like from a highly entangled quantum system, or to determine how much entanglement might affect proposed sources of quantum advantage, we can be able to form various quantifications or characterizations of how this proposed quantum sources for quantum advantage would depend upon noise, and how actually this is really consistent upon and elaborating further upon the paradoxical nature of quantum information and quantum physics together. And altogether, as we were discussing in the first presentation of the series, to begin our discussion of this group of topics, we introduced the noisy communication across quantum channels, which is dependent upon obviously the encoding and the decoding, as well as the transmission mechanism that Alice and Bob are using, over which they're distributing and sending these protocols from this classical bit information through a quantum channel. And also, this is drawing our attention to the fact that the action of the eavesdropper, Eve, on classical bit codewords can be transmitted by Alice or Bob. So basically, how successful or how much of a significant probability can Eve have in trying to place a codeword that she has tampered with into the authenticated set of bit codewords with at first finitely many bits and then obviously infinitely many bits over Alice and Bob's shared quantum channel. And this is establishing several connections with connections to optimization through primal feasible solutions of semi-definite programs. And obviously, anybody can see my most recent preprint or project and paper on the archive. I really delved into how this constrained optimization procedure can be used to characterize various notions of exact and approximate optimality, and really how, in a sense, this constraint optimization procedure through semi-definite programs that's taken with respect to the partial ordering of the positive semi-definite cone that I talked about and belabored several times in a previous presentation and series on my YouTube channel. It's even kind of relating to some type of constraint optimization procedure for the bit transmission rate, which is informing the converse result and the strict upper bound that we're obtaining in the converse result from the fact that we're taking a supremum over probability measures, as well as a minimum, a nested minimum, for one minimum being between the mutual information entropy and the conditional Shannon entropy, and then another minimum over the possible letters that Eve can use, which are entering into the condition of one of the conditional Shannon entropy terms. And the previous relevant work, like I've been describing, that I wanted to reiterate in quantum information theory is this paper that it's been under review at a very good journal that I'm hoping to hear back from soon. But they really have a lot of great topics that I felt was appropriate for this type of work. And basically, I was looking at characterizing exact and approximate optimality for XOR star and FFL games and how that relates to the CHSH and CHSH of N games given some restriction on the parameters n, which is coming into play from the number of players. And basically, this framework, like I described in the abstract for this paper, it's even generalizing another work due to Ostrev, due to the fact that we're looking at formulating well-posed semi-definite programs and then also introducing a suitable class of linear operators, which are used as intertwining operations. In this anti-commutation or this intertwining operation, it comes up in various and in fact several areas of mathematics and physics, mathematical physics, statistical physics, even in some other preprints that I have had in the archive that I've also submitted at other venues. I looked at how to formulate some type of weight matrix for a solid on solid model from the action of the R matrix on a tensor product of two intertwining vectors. And it's basically reversing, in some sense, the operation or the direction in which a tensor product is applied into this product of what's called these intertwining vectors, which is related to vertex models in mathematical physics and statistical physics. And it's really even rooted in relating to this type of collection of suitable operators that we study for this game theoretic sense to determine, roughly speaking, what would be the expected output or the expected result from reversing the order in which two operators corresponding to the set of possible responses that players can provide in response to questions drawn from a referee's probability distribution that would actually be of, more of an information theoretic interpretation or understanding. So I'm just mentioning all this just very briefly to say that there are just so many interesting connections when you look at the root in terms of how quantum physics can inform studies and research efforts into mathematical physics and also obviously into statistical physics and discrete along with integrable probability theory. And we're recalling the lower bound on the bit transmission rate provided in Ostrev's previous work. And this is really just given by the fact that, again, the original result on the bit transmission rate, not the converse result, which I'm going to provide and reiterate later in this presentation, is given by the fact that we're obtaining a lower bound for the bit transmission rate in terms of the supremum of this minimum over the entropies as well as the minimum over the conditional Shannon entropy, which we've described at several points, pretty much every presentation of the series, because again, it's very important just as we're describing in the overview part of the presentation of the series, because it's allowing us to determine what types of favorable properties would there exist for a decoding protocol for Alice and Bob so that they can map given different rates or different bounds or estimates or guarantees on what would be the bit transmission rate per single channel use of their quantum channel, and how that would actually relate to various properties of noisy error correcting codes, as well as how resilient would their probability of being able to minimize their false acceptance while actually maximizing their probability of being able to implement suitable error correcting codes. So there's just so many different types of potential applications and interpretations like we've been talking about. And obviously how, like I mentioned and alluded to in the previous slide, in this part of the series of this presentation, how that can have some type of interpretation with more of a mathematical physics or statistical physics type of leaning, if that's what the person or the researcher is interested in. And the converse result in the bit transmission rate is given again just by taking the two objects that were defined in the previous slide, but reversing the inequality. And obviously, even though it's just reversing the inequality for the direction of the bit transmission rate, in which hence in this point we're looking at a strict upper bound for a possible converse result on the bit transmission rate, it's really having a lot of different types of implications with regards to, again, besides being able to have some type of quantification or some type of estimate about the total number of qubits that one would hope to use per single channel use of a noisy quantum channel. Namely, there's more presence of noise over Alice and Bob's shared quantum channel in comparison to Bob and Eve's shared quantum channel, that there's actually a lot of intricacies like I've hoped to convince the viewer of, depending upon looking at this constraint optimization problem and taking upper bounds, formulating strict upper bounds for this constrained optimization procedure over probability measures, and also as taking the minimum, a supremum over probability measures, and also obviously a minimum over conditional Shannon entropy terms in the minimum over Z, as well as the mutual information entropy terms. And again, the explicit upper bound from the bit transmission rate obtained in the converse result from my new upcoming work is given by this, and that we're looking at log, and log contributions, where we're looking at, again, conditions which are being incorporated with the overlap function, which serves as a generalization of a counterexample that was provided in Ostra's framework on composable security without a secret key, namely being able to ensure some type of security guarantees or some security conditions, which is ultimately reflecting upon the fact that maybe in the presence of more or less noise, there's still a very good probability, a very high probability at that, of Alice and Bob being able to decode classical bit code words that are transmitted over their quantum channel from some suitable class of encodings. And obviously, beside the fact that to be able to maintain prospective quantum advantage as much as possible, Alice and Bob, they may have to eliminate spurious letters, which Eve could end up using in her probability distribution to try to introduce some type of corrupted message over their shared communication and their transmission mechanism over their quantum channel. It's really relating to other types of, like we've been mentioning, exact and approximate notions of optimality in game theory, namely the optimal strategies or courses of action that different types of players can take for maximizing their winning probability, or even interacting with a referee or interfacing with a referee who's making use of a scoring predicate so that some type of desirable, favorable outcome with regards to an information processing task can be achieved. And this again is given by the semi-definite program formalism of primal feasible solution Z prime, where we're looking at the game matrix times some objective Z prime, and we're taking, again, like we mentioned, a bunch of conditions that are taken with respect to the partial ordering of the positive semi-definite cone, in addition to the fact that because this is the primal feasible solution Z prime for the 3 XOR game, it's given by the fact that we're looking at 3 constraints with little I between 1 and 3, and asserting that for some other type of objective f sub I, which is multiplied by the game matrix, that for each one of these i's, the product of those 2 matrices is identically equal to C sub I. And we can form a semi-definite program duality gap formalism given primal feasible solutions Z prime and the dual objective S sub I just by taking the objective that we were performing the constraint optimization procedure over in the previous slide and subtracting off the summation over I of Y sub I, F sub I. And again, this is just relating to, because we've been talking about communication protocols and the probability of being able to execute these protocols with high certainty or a high security estimate or a high security, I don't know what the right word is, or high security guarantee, I guess we could say. This is really relating to some previous work from earlier in the year, like around not even 2 months ago, like a little more than a month and a half ago, in which I was pretty much describing, as is given in this screenshot of my preprint on the archive, quantum strategies, error bounds, optimality, and duality gaps from multiplayer XOR star, compiled XOR star, and strong parallel repetition of XOR star, and FFL games. So it's pretty much demonstrating how these information processing questions and tasks that I've been trying to motivate and describe for the viewer and for the interested people who are checking out these videos, how that's really relating to a lot of the information processing tasks that I looked at in a previous work. And albeit the fact, obviously, that this type of work didn't exactly consider bit transmission rates or decoding or encoding protocols, it's kind of very much related to the fundamental aspects of how players would be looking to, or would be interested, or would be privy about with regards to quantum aspects of information that they could leverage for potentially having proposed sources of quantum advantage. In parallel repetition of the optimal value of the XOR game stipulates that omega, namely the maximum winning probability of some parallel repetition of an arbitrary number of rounds of the XOR game, parallel repetition with itself of this game, is identically equal to omega of this parallel repetition of the XOR game, which is identically equal to the product of the maximum winning probability times raised to the number of strong parallel repetitions, which is indexed with little j. And dual semi-definite programs with objective y are really given by this type of expression. And I mentioned this more in the presentation in the series on the channel that was given in the last paper, but I really feel like it's helpful and interesting to discuss and to highlight because it's really demonstrating how at the heart of several quantum information processing tasks is the result, is basically a fact or a statement of a constraint optimization procedure with respect to this partial ordering of the positive semi-definite cone, and really how incorporating this type of probabilistic constraint that we've been talking about appears in the original as well as the converse result for the bit transmission rate is related to ultimately introducing some type of probabilistic constraints of a different type of nature for this dual semi-definite program under ordinary strong parallel repetition. And this is given by the fact that in the summation, we're taking the parallel repetition of the questions for each individual repetition of the XOR game, as well as looking at this against some dual objective function, which is dependent upon the specific distribution of questions that are distributed, that are picked at random, uniformly at random, from the referee's probability distribution of all questions every time that we're playing the game. And obviously, we're looking at an infimum where the constraints that we're incorporating into this infimum are given by the partial ordering, are taken with respect and with regards to the partial ordering of the positive semi-definite cone. And under strong parallel repetition, we also have the fact that, as characterized for many game theoretic situations, the action of a suitable operation, which, like I had mentioned, it's really fundamentally relating to the Heisenberg uncertainty principle and just basically various ways to try to interchange or anti-commute the order in which tensor products, or in this case, even parallel repetition operation of tensors that players can form for their responses in response to the referee's probability distribution, in which we have a sub I and a sub I prime, which is just given by the parallel repetition operation applied to 2 rounds of parallel repetition for the tensor observable or the set of possible responses and questions that Alice can provide for questions I and I prime that are drawn from the referee's probability distribution, which is forming its own type of operator that's being acted upon with a tensor product with the identity operator times this suitable operator script t. And we can see that in the remaining term, which is being subtracted under this inequality, we're anti-commuting or interchanging the order in which these terms appear, as well as performing some type of transformation to the strong parallel repetition operation 2 times that we had applied to Alice's observables in response to the questions I and I prime that are respectively drawn from the referee's probability distribution. And then this difference is acting upon the optimal solution or the optimal strategy for winning a parallel repetition of the FFL game with itself 2 times. And again, this is relating to a positive semi-definite conditions from the partial ordering of the PSD, the positive semi-definite cone. And as an example, such a statement from that previous paper that I've been describing for the viewer that's already been up on the archive for around 2 months, we're just basically saying that under the assumptions of the previous result, namely the ability to formulate a well-posed semi-definite program of this form under ordinary and strong parallel repetition, one can have the assumption that the following operator is just basically positive semi-definite. So that's just pretty much where the root of the constraints of the optimization procedure are entering. And for bit transmission rates that are not included in the converse result, we had also been describing how the probability that Alice and Bob map code words with high probability into the authenticated set of all code words is dependent upon the following. So basically, in the previous result in Ostra's framework that was written before I was considering and thinking about the converse results and the strict upper bounds on the bit transmission rate, his the soundness and the security estimates and also the guarantees with high probability of the decoding protocols that he introduces for Alice and Bob, it's dependent upon this following condition, namely the probability that there exists some C sub little n that's strictly positive, such that the cardinality of the authenticated n-bit messages from Alice and Bob over their shared quantum channel divided by or normalized in the cardinality of the authenticated n-bit messages by Eve over the quantum channel that she shares with Bob is much larger than C sub n. So pretty much that's underlying the perspective quantum advantage. And unfortunately, obviously, in the presence of noise, this type of perspective quantum advantage could potentially be ruined because, I mean, it's just a general fact for a lot of aspects of quantum algorithms that obviously, if you introduce much more noise into the system, you may, tamper with or unfortunately negatively impact the fidelity or just being able to have various types of algorithmic guarantees on maybe whether algorithm can be compiled in polynomial runtime. So there are various ways to characterize these types of dependencies of these quantum information processing tasks and these information processing protocols, you know, obviously in the presence of noise. In a previous result, which we had belabored quite a bit, like we've been describing at a couple of points in this presentation, is the previous result due to Ostrev based upon the transmission rate of bit cohorts for mapping into the authenticated space, like we've been describing, or the authenticated set of all cohorts with high probability. So again, just to very briefly reiterate, we're talking about the existence of a suitable protocols for Alice and Bob so that bit cohorts transmitted over their shared quantum channel can be mapped into the set of authenticated messages with high probability. So just basically fixing two parameters P and Q, which satisfy this condition, which is resulting in terms of the probability of bits of the classical code word being flipped when they're sent and they're transmitted over the transmission or mechanism over Alice and Bob's quantum channel or even over Alice and Eve's quantum channel. We're having some type of strict upper bound depending upon the difference of these two entropy terms from the bit transmission rate, and it's asserting that there's this protocol which is identically equal to Alice's policy for decoding n-bit cohorts as well as Bob's policy for decoding n-bit cohorts, so that just basically from script n of PQ, you can map into the authenticated space or the authenticated set of all bit cohorts with high probability for finitely many bits little n. And Eve's authenticated set over the quantum channel that she shared with Bob must be combined with the authenticated space or set of all bit cohorts over Alice and Bob's quantum channel. And I mean, this is just given the fact that obviously Bob and Eve, they have to introduce some type of, or Eve has to introduce some type of authentication protocol or some type of suitable protocol so that she can hope to transmit her corrupted message that she's eavesdropping on into the authenticated set of messages over Alice and Bob's shared quantum channel. And again, like we've been describing in that, I'll probably just go a little more quickly over because we mentioned it in the previous two presentations of this series, is that we have a favorable property of noisy error correcting codes, namely given the fact that we can define these two Hamming balls, we can also have these two associated transmission mechanisms over Alice and Bob's shared quantum channel as well as Bob and Eve's shared quantum channel, such that the ratio of these two conditional probabilities conditionally upon the fact that respectively some code words C sub 1 and C sub 2 are transmitted over Alice and Bob's and Eve's shared quantum channel respectively, is bound below up to constants from some ratio of the noise levels of their two channels. So this is pretty much, again, really highlighting some type of remarkable or unexpected or paradoxical aspect of these error correcting codes and how we would expect for such codes in such admissible and favorable classes of error correcting codes to behave in the presence of noise. And then again, this is just to say that this script C term, which is coming into play in terms of this ratio of conditional probabilities that's given in the last slide, in this transparency, it's given by the fact that it's an intersection with the Hamming balls. So just basically the total number of words from the set of all possible code words from the code word superset, which is given by identically being equal to a union over all code words, as well as just basically also being identically equal to a union over all code words and bits of infinitely many bits that are transmitted over the transmission mechanism from Alice and Bob's shared quantum channel and Bob and Eve's shared quantum channel. Informally, the set of all suitable error correcting codes for infinitely many bits has the following action. Namely, as we described, we're hoping to be able to provide guarantees or estimates or valuable, favorable properties of error correcting codes in the presence of infinitely many bits for different types of code words. So we're looking at the limit as the little n goes to positive infinity for infinitely many bits of the union over all codes where each one of the codes is correcting n-bit code words. which has the effect of increasing the authentication probability of accepting a code word that's being transmitted over Alice and Bob's shared quantum channel. Namely, the action is given by the action of the suitable class of error correcting codes on some type of code word C is equal to another code word C prime if and only if in the presence of infinitely many bits as little n tends to positive infinity, the n bit code for the n bit code words C and C prime, the probability of accepting C prime into the authenticated set of Alice and Bob's quantum channel is strictly larger than the probability of accepting the original code word before we're implementing and letting the error correction code maybe potentially detect bit flips or phase errors. That is larger than the probability that it was going to be accepted into Alice and Bob's authenticated set over their shared quantum channel originally. And one direction related to being able to perform error correction with high probability is related to the following, namely that when we're looking at the limit of infinitely many bits, we can look at the following probability, which should be identically zero, namely the fact that we don't want there to be a positive probability that there's some encoding as well as some decoding, which belongs to the authenticated set between Alice and Bob's quantum channel. For all encodings, there exists some for which there exists some decoding, but for which this condition is held. So pretty much we can formulate, obviously, and like I have in my project in my upcoming preprint on the archive, several different types of ways to make use of either the conditioning of code words and various types of probabilities, as well as probabilistic statements and proxies, if you will, or representations for the probability of error correction, as well as the probability of false acceptance. And we can decompose the probability of false acceptance over bits and instances of false acceptance. Namely, given that the fact that the probability of false acceptance can be identically expressed in terms of the probability of all the classes or instances of false acceptance over infinitely many bits, which is identically being equal to the union over all bits, as well as the union over little fa and big F of A, which is just given by all instances of false exception, which can be, unfortunately, one source of error in which there can be maybe some uncertainty with regards to whether there can be some type of suitable decoding protocol for mapping into the authenticated set with high probability. And again, we had described that in terms of the upper bound for the strict converse upper bound, what's coming into play for the bit transmission rate, other related observations that are performed near the beginning of the proof for theorem one, namely given the fact that we can look at some constraint optimization procedure like we've been mentioning from the supremum over probability measures and strictly upper bound this in terms of the log of the constraint optimization problem, as well as distributing the log term to each one of the constraints in the optimization problem, as well as actually being able to distribute terms further from the second term from the minimum over the conditioning in the Shannon entropy terms, because the log of the min of z is equal to the min of the min z of the log, as well as being able to make use of other various information theoretic consequences and properties of the mutual information entropy, as well as the conditional Shannon entropy that we've been describing for the viewer at a couple of parts of the presentations in the series. In the statement of the first main result, like we had described as theorem one, namely that we're having that there's a converse result on the bit transmission rate R for communication between Alice and Bob over a noisy quantum channel. And one has that the converse result, like we've been demonstrating in terms of the log and the log contributions and those factors holds. And specifically under this strict upper bound for the bit transmission rate, Alice and Bob can guarantee that with arbitrarily small probability that the decoding and false acceptance occur. So just basically they're able to minimize also simultaneously in the presence of greater noise the potential sources of error, which could threaten or could actually make less useful the aspects of quantum information, which could impart some advantage in terms of the information processing tasks that they're interested in pursuing. And again, this is just a statement of the second main result, like we had described. It's a kind of a longer statement that we had broke down at the previous presentation, the earlier presentation in the series, because we were talking about and describing a stochastic domination result of error correction false acceptance probabilities for communication over the quantum channels shared by Alice and Bob and between Bob and Eve. Namely, under the assumption that, like how we're defining in the slide, we're looking at greater noise being present over Alice and Bob's shared quantum channel in terms of Bob and Eve's shared quantum channel. And this is really relating to the fact that we're looking at the probability of error correction as well as the probability of false acceptance over Alice and Bob's channel and also over Bob's and Eve's quantum channel. And this is really given by the fact that, as we're demonstrating here, overall instances and suitable codes of error correction within the larger class EC over Alice and Bob's quantum channel, capital EC. This is identically equal to the supremum of the success probability of a player, Alice or Bob, using an error correcting code over their shared quantum channel, as well as the probability of false acceptance being identically equal to the infimum of the failure probability of a player accepting a message that should not have been accepted over Alice and Bob's quantum channel. And this is just basically given by the fact that the probability of error correction and the probability of false acceptance, as defined over Alice and Bob's shared quantum channel, can also be defined as some straightforward counterpart over Bob and Eve's shared quantum channel. And the continued statement of theorem 2, again, just to provide a type of broad statement in the last presentation of the series for the main results, like how we have been discussing in the previous presentation of the series, is that the probability of false acceptance over Alice and Bob's shared quantum channel is proportional to, and it's definitely related to and correlated to some instances of the probability of a decoding error occurring over their channel, which is identically equal to the supremum over all instances of decoding errors over Alice and Bob's shared quantum channel, namely of the decoding error probability of a message transmitted over Alice and Bob's quantum channel, as well as just a straightforward counterpart to these two probabilities, instead defined over the shared quantum channel between Bob and Eve. And altogether, one has the following stochastic domination of error correction and false acceptance probabilities, namely these two inequalities which we had described in the previous presentation of the series, namely the probability of error correction between Alice and Bob's quantum channel stochastically dominating the probability of error correction over Bob and Eve's quantum channel, as well as just taking the ratio of the probability of error correction over Alice and Bob's quantum channel with the probability of false acceptance over Alice and Bob's quantum channel. And obviously, besides the theoretical implications that we've been talking about, several applications of noise resilient protocols, or at least protocols that researchers hope are resilient to noise, can be applied for several algorithmic purposes. So I'm going to maybe describe some other types of applications of quantum algorithms and how they can kind of almost be thought of, roughly speaking, as entering into some type of correspondence or some type of similar favorable properties that we had discussed for regards to the probability of a false acceptance, authentication probability, and false acceptance probability. And this is just really going to the fact that I've discussed in a couple of different presentations across my channel, from APS March meetings, as well as an applied math seminar at Dartmouth, as well as even other types of seminars in which, or other types of topics of discussion relating to seminars that I've seen that can be used to relate or to make various connections between quantum computation, maybe computational biology, or even performing time evolution in general. And a lot of the interest, or more intense interest, I guess, over the past couple of years for quantum algorithms is that there's connections with variational quantum algorithms, VQA, or variational quantum eigensolvers, as well as quantum chemistry, electronic structure computations, which can relate to binding affinities. And I really had quite a bit of experience, just more as a computational biologist and a data scientist, in terms of looking at binding affinities, as well as really looking at performing these types of computations, which pretty much is, a type of constrained optimization problem over the set of all possible structures and proteins that I've even performed in a lot of consulting work for an NSF grant submission that we had gotten pretty far along into in terms of the submission and the application process. So there's very much a lot of interest in terms of determining what would be the runtime of these types of algorithms and how that would relate to maybe potential ways in which we could leverage algorithms for being able to obtain some more type of knowledge or characterization or classification of just basically what types of molecules would be optimal for different types of purposes. In a previous video that I described on implementing molecular docking simulations for novel compounds with Autodoc Vina was looking to establish a lot of types of connections between wide variety of compounds that can try to be optimized, that we can try to optimize over, determine the optimal structure and design over, and how this relates to, say, the crystal structure that I've discussed in a couple of different presentations for the COVID-19 receptor. So this is just basically one type of receptor and mutations to this receptor and its surface structures that have been gaining a lot of have obviously garnered a lot of influence because there were very negative impacts and, negative ramifications for healthcare and obviously several other types of areas of the economy and just our normal lives that were impacted from various mutations, which were imparted upon a known crystal structure that could really significantly increase the probability of infection for different viruses, which is obviously in general very interesting for virologists or other computationally minded scientists to investigate. And again, this is even relating to the fact that from a synthetic biology lab that I used to work of in my master's, my colleague David, whose picture is shown in this upper corner of the slide here, he gathered a lot of measurements from assays that were given from synthetic biology from parts of his workflow that I presented on different types of APS March and April meetings, in which he was discussing how to be able to perform experimental readout and data acquisition, which is almost very much like the type of problem that we want to look at, maybe not from as much of an experimental perspective, but more from a theoretical perspective for information processing tasks, in which basically David was interested in looking at different promoter barcodes and different CRRNA barcodes, which are just given by some inspection sequence that an enzyme investigates when it's looking at and scanning the genome for determining potential targets as it's diffusing either along an RNA or a DNA template strand. And this is given by the fact that from CRISPR-Cas nucleases, namely maybe catalytically active or catalytically inactive nucleases, which determines whether a cleavage step occurs when some enzyme is targeting some site of the genome that's of interest to explore to target for maybe performing genetic modifications. Even his assays could be of interest for quantum computation and being able to try to determine maybe whether there could be any unexpected fitness impacts, which is given in the second data that he had gathered from the lab that we used to work at together, in which there are many boxes within the possibilities of the promoter barcodes and the CRRNA barcodes, which are highlighted green, which is really impacting some significant increase in the abundance of different types of log of 10 counts, which is really rich, which in terms of this crosstalk map is imparting that maybe there's some unfavorable impact or characteristic of looking at different pairs of promoter barcodes with CRRNA barcodes for various Cas nucleases. So basically being able to maybe interface or make use of some quantum mechanical assumptions could help establish and bring more light upon these types of experimental aspects, like my colleague David from the lab that I used to work at in the Applied and Engineering Physics School at Cornell, and how this relates to maybe more theoretical studies that one could pursue in terms of electronic structure and structural biology together. And this is even related to the fact that in other work that I've done, obviously more on the theoretical side, I looked at in a couple of my preprints that have been up on the archive for a while, and even what I've discussed in other presentations on the YouTube channel, expansions of two-dimensional transfer matrix in large N limits from products of L operators. And obviously, I'm not going to go into this whole topic of discussion now because I have a lot of videos that the viewer can check out for those types of things and how it relates to quantum scattering. But it's pretty much relating to looking at fundamental processes of quantum physics and quantum information theory, because the double slit experiment in determining how interference patterns emerge when we're scattering different particles and measuring those quantum mechanical effects is pretty much coming into this very formalized and very theoretical and very involved at that framework in terms of making use of the quantum inverse scattering framework, or the quantum scattering framework for short, which is dependent upon the computation of the Poisson brackets of these block representations of transfer matrices, which are dependent upon these spectral parameters u and u prime. And this is even relating to the fact that rather than looking at the expansion of the two-dimensional transfer matrix, there's even another work that I'm still editing here and there for transfer matrices and products of L operators for the 20 vertex model in 3 dimensions over the triangular lattice, which is pretty much looking at, in a sense, a higher dimensional analog of the quantum scattering approach. So it's pretty much just demonstrating how a lot of these types of favorable algorithmic conditions that can almost be translated and made sense of in some way from a thermodynamic interpretation or some type of thermodynamic related quantities from statistical physics, and how that can relate to some formalisms that have been previously studied in seminal works from mathematical physics. And altogether, these types of conclusions that we've been describing, whether it's more of a theoretical information processing task or more of an applied algorithmic sense that I've been discussing at various presentations and drawing the attention of the viewer to at the end of the series, is allowing us to make associations between different types of systems. For instance, we can look at performing some genome mining task, or maybe more of a classical computational task with bioinformatics to determine whether from the SARS-CoV-2 receptor or the influenza virus or the Zika virus, there can exist some type of information which we can establish from a quantum mechanical perspective from the structure of, say, the COVID-19 receptor or the structure of some other pathogen, which could have maybe some high probability of infection that we would like to understand further, and how this relates to different types of receptors which we can characterize, which I've talked about across many videos in my YouTube channel. And so the conclusion that we're going to close out with is that we introduce encoding, decoding, transmission, and authentication protocols that are resilient to the presence of noise. And altogether, to further elaborate upon the conditions under which prospective quantum advantage is expected to hold, we introduced regular and converse results of the bit transmission rate, and we related the bit transmission rate to relevant information processing tasks, quantum information processing tasks at that. And this is allowing us to discuss how the bit transmission rate converse upper bound relates to the overlap function, namely, like we had described many times, the overlap of the alphabet or the common number of letters that Alice, Bob, and Eve use when they're responding to questions that they can, or information that they can transmit through classical bit codewords over their two respective shared quantum channels. And again, in the last couple of presentations of this series, to kind of give the viewer a very brief type of intuition or feeling or, idea about how quantum information processing tasks can be applied to, synthetic biology, computational biology, structural biology, as well as bioinformatics, in addition to maybe looking at other types of ways in which receptors can be studied and classified more thoroughly. We established rough comparisons with quantum algorithms, which can be ran in polynomial time, and which ultimately are relating to constrained optimization procedures from cost functions and different types of related objects that we're introducing in those optimization frameworks. And obviously, in future work, it continues to remain of interest to further study and to classify dynamics of quantum systems that can be mapped to next generation quantum processors and computers, hopefully with hundreds of logical qubits. And thanks so much for watching.